Hi there! Welcome to the 7th episode of the Digital Electronics Fundamentals series. Today we will talk about making a modular digital mini-lab. This device will help us run experiments on digital circuits by providing the means to build a circuit on a breadboard and power them up. Additionally, it will provide access to generate inputs and view outputs in digital formats through LEDs. This mini-lab is a great tool for students, hobbyists, or anyone who wants to learn about digital electronics. The one shown today consists of a power supply, a breadboard, LED set, switches and push buttons. The power supply will provide the necessary voltage to the circuit on the breadboard. The breadboard will be used to build the digital circuit, and the LEDs will help us to see the output of the circuit. The push buttons and switches will be used to generate input signals to the circuit. This way, we can manually control the timing and duration of the signals to test different scenarios. We can also connect external devices, such as microcontrollers or sensors, to the breadboard to test their interactions with the digital circuit. The LEDs on the digital mini-lab will indicate the logic levels of the output signals. By observing the LED patterns, we can understand the behavior of the digital circuit. And overall, the digital mini-lab is an excellent learning tool that allows us to experiment with digital circuits in a practical and intuitive way. So let's start building our own digital mini-lab to continue exploring the fascinating world of digital electronics together. The digital mini-lab is made of separate modules that can be arranged and connected together depending on the necessities. This modularity allows for flexibility in configuring the lab for different projects and experiments. Each module serves a specific function, such as providing power, signal generation, or output visualization. In this episode, we will build and assemble together 5 different modules. These modules will provide the means to build the circuit on a breadboard, power them up, and provide access to generate inputs and view outputs in digital format through LEDs. But that's not all. In later episodes, according to our necessities, we will keep adding new modules to expand the capabilities of the mini-lab. So let's take a closer look at each of today's 5 modules and how they work together to form a complete digital mini-lab. Here is the drawing of the first module of our digital mini-lab. All modules will have the same size and identical side panels, while the top panel will be specialized depending on the module's function. The side panels have big holes to allow wiring between modules, while the small holes are used to connect modules together using screws of size M3. For this module, the top panel has 2 big holes for binding posts to connect the mini-lab to an external power supply. Power will then be distributed to the other modules through wires underneath and through 2 pin headers on the other pin holes of the top panel. And to protect the contents of the module, we have a cover that will be attached to the bottom. Here is the 3D printed power supply module. The module is designed on the top panel with 2 large holes for binding posts and smaller holes for a pin header to connect power to the breadboard and other components. The larger holes on the side panels will be used to pass through power supply wires to power other modules of the mini-lab. The smaller holes on the other end will be used to attach the modules to each other using M3 screws. We also have the back cover for the case, which will be used to enclose the completed circuitry. Once all the circuitry is completed, we can attach the cover to the back of the case with 4 screws. I also added some graphics by hand to the 3D printed module for the power supply, to indicate that each binding post is directly connected with a separate pin header. This saved me a lot of time, as I did not have to prepare the decals, apply them, and spray protective paint to prevent them from scratching away. A permanent marker was all I needed. The top panel of the mini-lab has 2 binding posts for connecting it to an external power supply unit, and also 2 4-pin headers for connecting wires to the various parts of the circuit being experimented. To assemble the top panel, first insert the pin headers into the two slits, then use hot glue to hold them in place. While the glue is cooling, mount the two binding posts on the panel. Note that the holes for the binding posts are not circular. This is so that the binding posts will not be able to rotate when you tighten the nuts. Once the binding posts are in place, tighten the nuts, and then use hot glue to secure the nuts in place. Wait for 20 minutes for the glue to harden completely before continuing. Once the glue has cooled and hardened, you can make the connections between the binding posts and the pin headers. Cut a piece of wire and strip the insulation off one end. This will allow you to connect all the pins of the header together. Make a ring with the other stripped end of the wire and put solder on it to make it rigid enough to fit securely on the binding post. Then tighten the nut on the binding post to further secure the wire in place. Next, we need to solder the other ends of the wires to their corresponding pin headers. While soldering, it is essential to keep the wires in place by inserting them in a zigzag pattern between the pins of the header. Once all the connections are in place, the power supply module is ready to use. Simply connect an external power supply to the binding posts and use the pin headers to distribute the power to the circuit components on the Minilab. Let's take a closer look at the Breadboard module. It's the simplest module we will build, featuring a flat top panel with no additional features, and this allows us to easily attach a breadboard of standard size and use it to mount the circuits we want to experiment with. Like the power supply module, the rest of the case is identical with standard side panels. This allows all the modules to be attached together and wired by passing the cables through the large holes. Additionally, the dimensions of the modules are designed to fit exactly 3 modules arranged at a 90-degree angle with the long side of a panel. Here is the 3D printed breadboard module, featuring a flat top panel that is designed to accommodate a standard-sized breadboard that we can glue onto it. The side panels are identical to the previous module and will be the same for all the modules we will build. Here is the breadboard that we will attach to the top panel. To attach the board, we just need to remove the paper from the bottom to reveal a sticky pad. Carefully center the breadboard on the panel and then press down firmly to make it stick. Be cautious while doing so, because once the breadboard is attached, it cannot be removed without breaking it, as the sticky pad is very strong. The enclosure for the LED module is designed with simplicity in mind. It features 8 holes for the placement of LEDs and a slot for positioning an 8-pin header. I have opted to use 8 LEDs in this module so that we can display an entire byte of output from the circuit being tested. If more LEDs are needed, instead of creating a module with larger number of LEDs, which would lead to overcrowding the case, I recommend adding more modules like this one to the Minilab. Here is the 3D printed case, which includes 8 holes for the LEDs and a slot for the pin header. The pins will be connected with wires to the output of the circuit being explored. When the wire carries a high signal, or a logic level 1, which is equivalent to +5 volts, the corresponding LED will turn on. Conversely, when the wire carries a low signal, or a logic level of 0, which is equivalent to the ground connection, the LED will remain off. This simple yet effective setup will allow us to easily visualize the current status of the circuit being tested in the Minilab. Here is the graphic on the top panel indicating that each LED is controlled by a signal that can be inserted in a specific hole of the pin header. To mount the circuit that controls the LEDs and LEDs themselves, we will use a couple of strip boards that will be cut to size to fit inside the case. The strip boards will be attached together to make the equivalent of a single board. To prevent drawing excessive current from the circuit under test, each LED will be powered by an individual transistor, with each transistor being controlled by a specific pin on the pin header. The 22K resistors ensure the current drawn from the circuit under test is kept to a minimum, while the current flowing through the LEDs is limited by the 120 ohm resistors connected in series to the LEDs and the collector of the transistors. We will need to power this circuit through the power supply module, and the connections between the two modules will be established internally within the mini lab with wires passing through the inside of the cases. Here is the fully assembled circuit, completed with 8 LEDs that will be visible through the top panel's holes. As you can see, the circuit board is made up of 2 separate strip boards attached together, and the pin header here will pass through the top panel. To test the circuit's functionality, we will connect the bench power supply to the wires and apply a logic 1 on the pin header using the wire connected to the positive 5 volts. This will allow us to determine if the LEDs turn on correctly. And sure enough, all of the LEDs turn on as expected when a signal is applied to the corresponding pin on the header. Here is the board fitted inside the case module. To secure the board in place, I will be using a few drops of hot glue. The glue needs to be applied at several points along the perimeter of the board to ensure it won't move when the mini-lab is handled and used. Okay, the glue has now hardened. However, when I push on the LEDs on the edges, I notice that they can move slightly. To prevent this, it's better if I add some more glue to the corners. Here is the module that provides 8 switches, each of which can be set to either 1 or 0. The output of each switch is made available on an 8-pin header. The panel of this module features 8 holes for the switches and a slot for the pin header. The design of this module is consistent with that of the other modules. Here is the 3D printed case for the switches module. The sides of this module are identical to the other modules. On the top panel you can see the 8 holes for the switches and 1 for the pin header. Here is the same module with a graphic showing the connection between each switch and the corresponding output pin on the header. The graphic was manually drawn to make it easier to understand the functionality of the module. The switches module schematic involves some complexity due to the contact vibration that occurs when a switch is operated. These vibrations generate a train of electric pulses, which can lead to undesired effects on digital devices. To solve this problem, I adopted a hybrid approach that combines analog and digital circuitry. When a switch is closed, a capacitor discharges through a 1K resistor. This filters out all the temporary fluctuations of the signal at the switch. As soon as the capacitor discharges below the thresholds for changing the state of the Schmitt-Trigger inverter, a clean change of state occurs at the output of the inverter. Vice versa, when we open the switch, the capacitor charges through the 10K resistor. As soon as the voltage of the capacitor goes above the Schmitt-Trigger threshold, the inverter changes state again, generating a clean transition at its output. We need 8 inverters, 1 for each switch, but the SN7414 that I used contains only 6 inverters, and therefore we need to use 2 ICs, and the second one will have 4 unused ports. To avoid the random fluctuations of such ports, the input is always forced to be 0. With this design, the digital signals on the pin header will always be clean and precise. These are the switches I have chosen for this application. They are labeled with the digits 0 and 1, making it easy to understand their current state. The switches can be inserted into the holes on the panel and will lock automatically thanks to wings on 2 opposite sides. To install them, simply place them on top of their respective hole and push them in. A satisfying click will indicate that the switch is locked in place. Let's now install all 8 switches on the panel, making sure they are all oriented in the same direction. The next step is to assemble the circuit on a strip board, like this one, and we will also need to wire the switches themselves. Here you can see that I am soldering 8 pieces of stranded wire with yellow insulation onto the pins of the header. Once all the wires are attached, I recommend adding heat shrink tubing to insulate the pins and prevent them from touching each other. Once the pin header is wired, we can insert it into the slot of the front panel and secure it in place using hot glue. During this process, it is important to ensure that the pin header is flush with the surface of the panel. Once the hot glue has set, we can begin wiring the switches by starting with the ground connection. This wire will need to be connected to each switch and eventually connected to the ground of the circuit. To make this connection, I have used a bare wire and soldered it to the same connector of each switch. To connect it to ground, I have attached a black wire to one end of this bare wire. To mount the strip board, which will hold the circuit on top of the switches, I am using 4 spacers. I have screwed them to the 4 holes of the board. The other end of the spacers can be glued directly to the back panel. To do that, I put some glue on each spacer and then position the board in its final position. Once the glue has dried, we can unscrew the board and mount the circuit on it. The spacers will remain glued to the back panel to later support the finished board. To help find the optimal position for the ICs and connectors, we can temporarily position them on the strip board before removing it from the case. Once the glue sets, we can remove the screws to fit the board, and we can use the center connector of the board to attach the wires from the pin header, while the side connector will be used for the switch wires. With the board out of the case, we can now assemble the circuit on it, and then we can complete the wiring for the switches, put the board back in the case, and connect all the wires. To ensure that the spacers stay attached to the back of the panel, apply some additional hot glue around them. Here is the completed circuit of the strip board. The 2 ICs containing the Schmitt trigger inverters are visible on this side. And additionally, I added a note in front of the connectors to help remember which one connects to the pin header and which one connects with the switches. You can also see a third connector used for the power supply of this module, and for that I have indicated with a plus sign which side is for the positive power supply. Here is the wiring I just added for the switches, using green wire to distinguish the switch wires from those of the pin header. Initially I used solid wires, but later I decided to change them to stranded wires, as they are more flexible and less prone to break when securing them to the connectors. At this stage, I have not completed the assembly of this module, as I need space to insert screws on the side panel to connect all the modules together. Once the strip board is mounted inside, this module will not leave enough space to access the side panel screws. So later on, once the case is attached to the other modules, I will complete the assembly of this module and I will test it. The push-button module will feature 8 push-buttons, providing us with ample options for building test circuits in the Minilab. Each button can provide a signal that transitions from 0 to 1 when pressed, and another signal that goes instead from 1 to 0. The panel will have 8 holes for the push buttons and 2 slots for 2 pin headers, one for the 0 to 1 signals and another one for the 1 to 0 signals. The remaining aspects of the case will be similar to the ones we have already seen. And here is the 3D printed module for the push buttons, featuring the 8 holes for the buttons and the 2 slots for the 2 8-pin headers. Here is the module case for the switch buttons with hand-drawn graphics. The top slot is for the 1 to 0 signal pin headers, while the other slot is for the 0 to 1 signal pin headers. The push-button circuit is slightly more complex than the switch circuit because it needs to generate 2 different signals for each button. Just like the switches, push-buttons are also prone to contact bouncing, which can lead to a series of pulses instead of a clean signal transition. To overcome this, we will connect each button to a circuit that includes a capacitor, which charges and discharges depending on whether the button is pushed or released. The first row of Schmidt-Trigger inverters generates the 0 to 1 signals, and the output of each inverter is connected to another inverter that provides the 1 to 0 signals by converting each signal to its opposite. To accommodate a total of 16 inverters, we need to make space for a total of 3 IC SN7414, each providing 16 inverters. We will therefore have 2 spare inverters, which will have their inputs connected to ground for stability, just as we did in the switch circuit. Here is the circuit assembled according to the schematic we just saw. The only missing parts are the 3 ICs, which will sit on these 3 sockets. The board was made by putting together 3 pieces of perfboard. The space in the center will allow us to access the wires coming from the 2-pin headers, which will be mounted directly on the panel, similar to the switches module. Due to the crowded board, there is no space for connectors, and so I decided to solder the wires from the pin headers directly onto the board. Let's now mount the ICs on their sockets so we can complete the assembly of the board. When doing this, be careful not to inadvertently bend the IC pins, as they may not make contact with their sockets, and their circuit will not function properly. And now it is time to complete the assembly of the module. I have prepared the 2-pin headers with wires long enough to reach the appropriate places on the board. I used yellow and green wires to distinguish between the wires of the 2 headers. And I have also attached the spacers for the board to the back of the panel, using the same technique as for the switches module. So next, let's position and attach the 2-pin headers. Starting with the one with the green wires, apply some hot glue to the edge of the case, and then carefully position the header and apply more glue to the other side. Repeat the same process for the second header and apply additional glue to secure it in place. We will now wait for the glue to dry, after which we can proceed to complete the wiring of the module. Okay, the glue has now hardened and we can continue with the wiring. The green wires are connected to the pin header for the 1 to 0 signals, while the yellow wires go to the pin header for the 0 to 1 signals. We just need to carefully follow the schematic and solder each wire to the correct pin on each header. I made sure to leave enough space on the board to make the wiring process as easy as possible. With all the wires soldered to the board, we can now place it on top of the spacers and secure it in place with screws. Depending on the type of your perfboard, you may need to use a different number of screws. And to avoid alignment issues, it's best to insert all the screws before tightening them. Since this module needs to be powered through the power supply module, we'll test it after mounting it to the rest of the Minilab, which, now that all the modules are ready, we can begin to assemble right away. Let's start by assembling the power supply module and the breadboard module together. Remember that this digital Minilab requires a 5 volts power supply to work with TTL circuitry. However, the same voltage can also be used for CMOS circuitry. To mount the 2 modules, we will use 3 M3 screws along the longer side. If you are using my design for the module cases, the holes are already sized for M3 screws. You can find all the files with my design and the schematics on my website eleneasy.com. The link is available in the video description. To prevent the nut from sinking into the plastic of the side panel and breaking the panel, it's always better to add a washer before inserting the nut. And before tightening the screws, ensure that the cases are well aligned with each other. If they are not aligned properly, the Minilab will not sit properly on the workbench. Let's start testing the power supply module now. Our first step is to ensure that all the pinholes are properly connected to the 2 binding posts. We can check this by using a multimeter to test for continuity. We should hear a beep from the multimeter indicating that there is good continuity between each pinhole and its corresponding binding post. Next, let's mount the LEDs module on the right side of the Minilab. Ensure that the pin header is oriented toward the inside of the Minilab to make it easier to run all the necessary connections when assembling a circuit. We will only need 2 screws to attach the long side of the new module to the 2 short sides of the 2 modules already mounted. After attaching the module, we need to run 2 wires from the power supply module to the LEDs module to power it up. The wires will need to be routed through the larger holes on the side panels. Once the wiring is complete, we can test the LEDs module to ensure it works correctly, and to do this we will connect the power supply module to a workbench power supply set to 5 volts DC. Then we can use a breadboard wire to connect each LED pin to +5 volts and verify that it turns on. Let's now mount the switches module in the space below the breadboard module. It's important to do this before mounting the circuit board inside the switches module, otherwise it will be difficult to reach the holes where the screws need to be inserted. This time we will be using 4 screws, 1 on the shorter side and 3 on the longer side. And now, as you can see, I have already attached the new module to the Minilab. I also replaced the solid wires with stranded ones to increase flexibility and prevent connections from breaking while moving wires and the circuit board. We still need to add wires for the switches themselves. Depending on the distance between each switch and the connector on the board, the length of the wires will vary, so it is better to cut pieces of various lengths to limit the wire mess inside the case. And lastly, don't forget to prepare the ends of the wires with some solder to ensure that the strands don't spread out and cause any problem. After soldering the wires to the switches leads, position the circuit board on top of the spacers, and make sure to leave the wires accessible so that they can be connected to the board later. Secure the board in place using the 4 screws. Once the board is fixed, start connecting the yellow wires to the center screw terminal block, ensuring that they are in the right order, so that each switch refers to the correct output pin. After connecting all the yellow wires, use a multimeter configured as a continuity tester to verify that all of them are in the correct order. Connect one lead of the multimeter to a pinhole of the header on the front panel and the other lead to the corresponding screw on the terminal block. A beep will confirm the correctness of each of the yellow wires' position. Connecting the green wires requires checking each one individually, since the switches underneath the circuit board are not visible. To do this, use the multimeter to verify continuity. Connect one probe of the multimeter to the ground wire coming from the switches, and the other probe to one of the green wires. Then operate the switches until you find the switch corresponding to the specific green wire. Once you locate the switch and its position on the panel, connect the green wire to the corresponding position on the terminal block. After all the green wires are properly connected, connect the power supply using 2 additional wires, a red one and a black one. Connect one end of the wires directly to the pin headers of the power supply module, and the other end to the appropriate position on the terminal block for the power supply on the switches module. When connecting the negative wire, insert both the one coming from the power supply and the one from the ground connection of the switches into the terminal block hole. To test the switches module, we need to connect each output from the module to the corresponding input of the LEDs module. To do this, we can use jumper wires or breadboard wires. Once we have connected the switches and the LEDs modules, we can power up the Minilab from an external power supply set to 5 volts. Then we can start operating the switches. If a switch is in the on position, the corresponding LED should light up, and if a switch is in the off position, the corresponding LED should remain dark. This will allow us to verify that the switches are properly connected to the circuit board and are functioning correctly. At this point, we need to mount the final module onto the Minilab, which is the pushbuttons module. To begin with, cut a black and a red wire that are long enough to reach the last module from the power supply module. Afterward, solder one end of each wire to the power supply module. Next, install the pushbuttons module, ensuring that the two pin headers are oriented towards the center of the Minilab. Secure the module in place by inserting and tightening the 3 screws, aligning it with the other modules. Afterwards, carefully route the red and black wires from the power supply to the pushbuttons module and connect them to the correct position on the terminal block. It's important to make sure that the wires are connected with the correct polarity, as reversing the polarity could damage all the semiconductors in the circuit. It is now time to test the pushbuttons module. We can use the LEDs module again to verify the functionality of the pushbuttons. So first, connect each pin of one of the 2 headers of the module under test to a corresponding pin on the LEDs module. Starting with the header providing the 1 to 0 signal, all the LEDs are on at first. But then push each button to verify that the corresponding LED turns off. Next, test the outputs of the other pin header. This time the LEDs should start off, and whenever you push a button, the corresponding LED should turn on until the button is released. Once everything is assembled and tested, place the covers onto each module to protect the internal circuitry. Finally, add anti-skid pads to the bottom of the Minilab to prevent it from sliding on the bench surface during use, and also to protect the surface itself from being scratched by the screw heads. To demonstrate how the Minilab can be used to verify the functionality of digital circuits, we can construct a clocked SR flip-flop on the breadboard, like the one we studied in the previous episode. With the available features on the Minilab, we will be able to eliminate some components from the original schematic and use the ones on the Minilab instead. So, for example, we can remove the external LEDs and their series resistors, as well as the resistors and push buttons on the left side, since the Minilab now has its own push buttons and switches. For the inputs, we can use push buttons for S and R, and a switch for the clock input, which can remain in the same state while we operate the push buttons. As expected, while the clock is set to 0, pushing the S and R buttons has no effect. However, when we set the clock to 1, the S and R buttons start to work. If we repeatedly push one of the buttons, nothing else occurs until we push the other one. Returning the clock to 0 disables the S and R buttons once again. In this video we have demonstrated how to assemble and test a digital Minilab, which is a versatile tool for building, testing and debugging digital circuits. The Minilab consists of several modules, each providing a different set of inputs and outputs, such as switches, LEDs, push buttons and a power supply. We have shown how to connect these modules together, how to test them individually and collectively, and how to use them to build and test digital circuits. We have also highlighted some of the advantages of using a Minilab over a traditional breadboard, such as the ease of wiring, the built-in components, and the modular design. Finally, we have illustrated the use of the Minilab by building and testing a simple SR flip-flop circuit using the push buttons and switch available on the Minilab. This demonstrates how the Minilab can be used to verify the functionality of digital circuits and to experiment with different designs and configurations. Overall, the Digital Minilab is a valuable tool for anyone interested in digital electronics, from students and hobbyists even to professionals and engineers. It's easy to use, flexibility and modularity making it an ideal platform for learning, experimenting and also prototyping digital circuits. In future episodes of this series, we will continue to make use of the Digital Minilab, and we may even add some extra modules to it. To make sure you don't miss any of these upcoming episodes, I recommend subscribing to the channel and clicking on the notification bell to receive updates. See you soon in the next episode, and as usual, happy experiments!